Hey geometry students, today we are starting three-dimensional figures. Finally, we are getting out of the world of two-dimensional figures flat on the page, and we're going to be looking at things that actually resemble real-life three-dimensional objects. In geometry, we're going to call them solids, and they are basically bounded by flat or curved surfaces that enclose a single region of space. We're going to call that a solid. Now, certain solids are also called polyhedron if they are actually bounded by polygons, which we have been studying. And those polygons would be called faces. As you can see in the diagram, this solid that we're looking at has 6 faces. It has a front face, a back face, a top, a bottom, and a left and a right side face. And each face is a different shape. Okay. Another word associated with polyhedron is edge. Okay. There are many edges on each polyhedron, and an edge is basically a segment that is formed. That would be like a piece of a line, a straight segment, where two faces meet or intersect. Okay. Vertex is going to seem very familiar because we've always had vertices of polygons, but in this case, when you're talking about a solid, a vertex is a point where 3 or more faces meet. Now in a polygon, a vertex would be where like 2 edges meet, but in a polyhedron, where 3 or more faces meet, that would be considered a vertex. And you can see vertex, that's a point where 3 faces meet, the bottom, the front, and the left side. In the rest of this chapter, we are going to be looking at these 5 geometric solids. We're going to explore them in depth. We're going to find their surface areas and volumes and talk about what they're made up of. So 2 of these figures are polyhedron, and 3 of them are not. Prisms and pyramids are considered polyhedra because their faces are all just flat polygons. These cylinders, cones, and spheres are not polyhedra because they have faces that are curved. They are not flat polygons. And that's really the main difference. So let's start with being introduced to what is a prism. I know you've probably seen them before in middle school. They've been introduced to you, but we can review. A prism is a polyhedron with 2 parallel congruent faces, which we will call bases. Now let's not skip over that right here, 2 parallel congruent faces. There's a lot to unpack there. Each of these examples of a prism, we need to pick out the 2 faces that are parallel to each other and congruent to each other to verify that these are prisms and what kind of prisms they are, because actually prisms are named for their bases. Okay. Also, some prisms are considered regular prisms because they have bases that are regular polygons. And a regular polygon is a polygon which has all of its edges and interior angles congruent to each other. So, a triangular prism has 2 bases that are triangles. I'm just going to make it simple by drawing a little triangle there. And those 2 triangles are connected by 3 rectangles. The other faces besides the 2 bases are rectangles in a prism. Okay, so here is a triangle base and here's another triangle base. Those 2 triangles are congruent to each other and they are parallel to each other. They are sitting in such a way that they will never touch each other. They are parallel. Notice that the other faces, and I'm just going to change my color here to point them out, this face is a rectangle. And it's actually not parallel to any other face. You can see that it is intersecting with the bottom and the other side. But the bottom is a rectangle, the other side's a rectangle. So we can identify this as a triangular prism because the two faces that are parallel and congruent to each other are triangles. Okay. The one in the middle here is a rectangular prism. The definition of rectangular prism is a prism that has two parallel bases that are rectangles. And I'm just going to put real briefly a abbreviation there for rectangles. But those two congruent rectangles are connected by four rectangular faces, but they're also rectangles. So rectangular faces. Okay. Let's say four rectangles. But notice these have to be in this particular rectangle, if we think of it as being drawn to scale, those two sides must be considered the bases because they are the two that are parallel to each other and congruent. The other four are also congruent to each other, but if you call the top and bottom sides the bases of this thing, then your other rectangles are not all going to be the same. So a pentagonal prism would be one where the bases are pentagons, five-sided polygons. And those two pentagons, see the top here is a pentagon and the bottom is a pentagon? Those two pentagons are connected by rectangular faces. All the upright walls of that figure, you could call it, if it was like a box or something, the sides, those are all rectangles connecting the two parallel congruent pentagon bases. All right, on this part of the page, we have the formulas for the surface area and volume of prisms, basically any prism. Now, the example shown is a triangular prism because the base is a triangle and the lateral faces are the rectangles. The lateral faces are the other faces that connect the two bases together. So this is a new word here, lateral, that we are seeing on this screen. Oftentimes, a prism may not necessarily be sitting on one of its bases. Like this triangular prism looks like a Toblerone box. You ever have Toblerone chocolates? But anyway, it's not sitting on one of the bases. The base is actually this front side, this small triangle. And how do I know that? Because it is congruent and parallel to this other side that's a triangle. Okay, the three rectangular sides are not parallel to each other, so they're not the bases. Okay, now we're going to get back to these formulas and how to use them, but you'll notice that they probably look a little different than any prism formulas you may have learned in middle school. In middle school, you probably took a rectangular prism like this, and you probably talked about it in terms of length, width, and height, and you had some kind of surface area formula that was just adding up all six of the side areas, the faces. So maybe it would be 2 times the length times the width, because you've got the bottom and the top. They're both rectangles with length times width. And then you've got the side walls. That would be W times H, and there are 2 of them. And then you've got the front and back would be L times H, and there are 2 of those. So this would be the surface area formula that you're probably familiar with from middle school, but we're going to approach prisms in a different way so that we have one kind of formula for all different types of prisms, whether they are rectangular or triangular or pentagonal or hexagonal, excuse me. We're going to be able to use these formulas for any kind of prism, no matter what the shape of the base is. All right, we'll get back to that in a little while. But while we're here, I do want to point out that this lateral area, new vocabulary word, it's basically talking about the area of what would be considered the walls. Like if I were to take this triangular prism and I were to rest it like a Toblerone box standing tall on its little triangular base, okay? Oops, that's a triangle. Okay, so here's our Toblerone box sitting on its base, okay? These sides, these rectangular sides, these are considered the walls, like as if it was a big tall room, okay? The wall area is the lateral area. Then there's the area of the bases, okay? That would be this B value, area of one of the bases. Okay, so we'll practice that in a little. So before we get too deep into the formulas, I do want us to be able to recognize the difference between a prism and a pyramid today. We're not going to worry about circles, cylinders and cones and spheres today at all. That'll be in another lesson. We're just going to focus today on pyramids and prisms. So if you think about the word pyramid, many things might come to mind. The pyramids in Egypt, that's a really good example. They are the shape of a geometric solid that is a pyramid, okay? So a pyramid is a polyhedron where all of the faces except for one intersect at one vertex, and that would be the top point of the pyramid. So all the faces except for one, and that one is the base, okay? So that base is a very significant face for the pyramid because that is how you determine what kind of pyramid it is. Did you know that all pyramids are not square? The pyramids in Egypt are square. You can look it up, find an example. Go on Google Maps, look at pyramids of Egypt, look down. They have a square footprint if you look from above. Okay, but you can have a triangular pyramid, you can have a pentagonal pyramid, you can have a hexagonal pyramid, you can have any shape on the bottom, and all of the faces coming up to that singular vertex at the top will always be triangles. So all the other faces are triangles coming up to a point, and the base is what you name it after. So triangular pyramid has a triangular base. A square pyramid has a lot of triangles in it for the faces that come up to a point, but the base is a square, and that's why we call it a square pyramid. Okay, a pentagonal pyramid would have a pentagon as its base, and then it has lots of triangle faces coming up to a point from that base, but its base is what we name it after. And so here are the formulas for the area, surface area of a pyramid, the volume of a pyramid. They're over here. Surface area, volume, and LA stands for lateral area. The lateral area would be the area of just the walls without the base. Okay, so that's outlined here. These are the kind of key to the symbols that you see in the formulas, and we will practice that in a little. Okay, so just with an introduction to what is a prism and what is a pyramid, I would like you to look through these 8 figures and determine whether each one is a prism or a pyramid, or maybe neither. Maybe it's something else. Okay, so take a few minutes to think about that and answer the question in the video. All right, so if you really understand what each type of solid is, you should be able to envision how a 2-dimensional flat template could be transformed into that 3-dimensional solid. So these things are called nets. You may have seen them before, but what we want to do is be able to envision what kind of solid would be formed if we were to fold these 2-dimensional nets or templates or models into a 3-dimensional figure. So I have here the first one as an example, number 10. Okay, the idea would be that you could fold these 2 circles down like so, and you could wrap this around the perimeter or circumference of the circles, okay? And you would have, what would you have? Well, it's not actually a prism, even though it does have 2 congruent parallel bases that are circles, but just because it's not connected by rectangular faces, it's not considered a prism. It has its own special name. It's a cylinder, and you probably knew that. You're like, ah, we've talked about that before. But that's the idea. A net is a two-dimensional shape that you can fold into a three-dimensional solid. So number 10 is a cylinder. It is not a prism or a pyramid. I want you to think about what would happen if you were to fold along the lines on the inside of this net, fold these triangles up, and fold these top and bottom rectangles kind of towards us, okay? What kind of solid would be formed? And the same thing goes for number 12. You probably recognize this one. It's pretty popular, common thing to see if you were to fold it up. Okay, think about that. Okay, so our first example of actually computing the surface area of a solid, we're going to be working on this is not a rectangular prism, that's a mistake. This is a triangular prism. So you can go ahead and correct that if your notes say rectangular prism. This would be triangular. Okay. I know it's a triangular prism because the top and bottom sides or faces are triangles. They are parallel to each other. And the other faces are rectangles connecting them. So that makes it a prism. The two bases are triangular. Okay. Now, you could do this just by analyzing each of the shapes and kind of adding the different faces together to find the total surface area. For example, you could go for the top and bottom, both being triangles. You just have to calculate the area of the top triangle and multiply by 2 because you have 2 of those, top and bottom. Then you could look at this side rectangle over here, and you could find the area of that, and you could look at this rectangle here, find the area of that, and just find each area separately and add them all together. That is a completely valid way to do this. But we are going to use the formulas that you have on a page or two back for first finding the lateral area, which would be the area of just the walls of this, and then the entire surface area would be that lateral area plus the two bases, okay? So let's look at the formula. The first formula for lateral area of a prism is P, capital P, times H. Now, P, if you look at the key, stands for perimeter of base, and H stands for height of prism, okay? So you may want to make a note of that. You might want to kind of, for the first time here, just say perimeter of base. And H stands for height, not of one of the triangular bases, but the height of the entire prism. So the perimeter of one of the bases would be basically this. Okay, I'm outlining the top one because it's easier to see because it's right there on top, but it's also the same thing as this. These are the two bases. So we have 9 on one side, 8 on another side, and the question is, what is that third side? Well, thankfully, this is a right triangle, as indicated by that little right angle marking. So in order to do this perimeter, we are going to have to use Pythagorean theorem to find that hypotenuse or third side. Okay, I've gone ahead and done the Pythagorean theorem with 9 squared plus 8 squared because that's A and B. C is the hypotenuse. So A squared plus B squared equals C squared. 9 squared is 81, 8 squared is 64, C squared, we're just going to leave for now. Add these together, C squared equals 145. Then take the square root of both sides to get C, which is 12.04. That means the perimeter of the base is 12.04 plus 8 plus 9. So that's 29.04. Okay. So P can be filled in with 29.04. And then the height of the prism is the distance between the bases, which is 5 in this case. So the area of the walls, this rectangle plus that one back there, outline there, the lateral area is going to be 29.04 times 5, which is approximately 145.2. And that would be in whatever units squared, because this is area. So that is lateral area only. Now, if we want the entire surface area, we're going to have to take the lateral area and add the two bases, the area of each base, times 2, because there are two bases, plus the lateral area. Now, each of these bases is a right triangle, and that right triangle itself has a base of 8 and a height of 9. So in order to find the area of one base, we have to use the area of a triangle formula, 1/2 b times h. Notice I made this lowercase b. Lowercase b stands for the base of just a flat, solid side. Okay, capital B stands for the area of one of the bases. Okay, so the area of one of the bases here is just a triangle. So I'm going to plug it in over here. 1/2, the base is 8, the base of the triangle, and the height of the triangle is 9. Okay, so 4 times 9 is 36. So that means each of the triangular bases has 36 as its area, so that's what's going to go in for capital B. All right, now I'm ready to find the total surface area. I've got the lateral area is 145.2 plus 2 times 36. And that final answer for total surface area is going to be 217.2 units squared. Okay, the lateral area is always going to be smaller than the surface area because the lateral area is just the walls, the upright connecting rectangles that go between the two bases. And then the surface area is that plus the top and bottom, or the bases. Now, it may not be sitting on its top and bottom, but you get the idea. Okay, before we get into example 2, I feel like I failed to mention, why do we find surface area of a solid? Surface area is basically the amount of area that would have to be covered if you were going to, let's say, wrap this object up in paper, okay? That would be representing the amount of paper that you would need to cover all the surfaces. Or let's say you were going to paint something. How much paint would you need to cover the surfaces? That's what surface area is calculating for a solid, okay? So let's take a look at this pentagonal prism. And it says find the lateral area and surface area. If each side of the pentagon base has a length of 14 and the prism has a height of 8. Okay, with that information I can label the different parts of the diagram to start with. Each side of the pentagon is 14, like so. It does say pentagonal prism. I would assume it's regular pentagon, so all of the sides are equal and all of the angles are equal. And then the distance between the bases, oh, these down here are also 14, 14. The back here, this dotted line, that's 14, that's 14, that's 14, this is 14, this is 14. All of those sides of the pentagon are 14, but the height, the distance between the bases, is 8. Okay? Okay, so we're going to go back to starting with the formula. The formula for the lateral area of any prism, no matter what shape the base is would be lateral area equals perimeter of the base times the height of the prism. That's actually going to be pretty simple in this case because the perimeter of the pentagon is just 5 times 14. Okay, so that's 14 times 5, which is 70. And the height of the prism is 8. So we're looking at the lateral area is really quite simple to find here. It's 70 times 8, which would be 560 square units. Or I guess it would be inches, excuse me. Square inches. So that's the lateral area. If you just had this like pentagonal room, let's say, or, oh, hey, the Pentagon. Okay, the Pentagon building, it wouldn't be inches, it might be like, who knows, whatever those dimensions might be. If you just wanted to figure out how much you would need to cover the surface of the outer walls of the Pentagon building, that would be the number, 560 square inches of materials to cover just the outside walls, not the roof, not the floor, okay? All right, so if we want to now find the surface area of the entire solid, we're going to have to start with the lateral area and add the two base areas. So the areas of the two pentagon bases. All right, so it's going to be 560 plus 2 times whatever the area of one of those pentagon bases is. All right, I'm going to leave that there for right now, and I'm going to kind of come off to the side and talk about how to calculate the area of one of these pentagon bases. Okay, here we go. I'm just kind of looking at it now from above. The side is 14, okay? What I'm going to do is draw this center point and kind of sketch some radial segments going out from the center to each vertex. And then I'm going to draw this little line down the center here to make a little right triangle. Okay. That right triangle is significant because it can help us to calculate the area of these triangles, and a pentagon is made up of 5 of them, right? You can make from the center point to each of the vertices, you can make 5 equal segments, and then you've got this triangle is the same as all the other 4. So you got 5 equal triangles. If we can calculate the area of that one triangle on the bottom there, I'm going to put it in red, okay? Then we can get that times 5, and it's the area of the entire pentagon. Okay, but finding the area of that triangle, you'll notice that I've blown it up here a little bit. It's going to be a little bit complex. For a pentagon, what we're going to do is, first of all, recognize that the 14, that is the length of each side, would become the bottom of this triangle. Okay, so we know the base of the triangle, and ultimately we are trying to be able to calculate the area of this triangle, 1/2 its base times its height. I know that the base is 14, so that's going to be 1/2 14. But now I need to calculate this height to put it here so that I can have one of these triangles and then multiply that by 5 for the entire pentagon. Okay, so this is now my question. How do I figure out that height? I'm going to use trigonometry. Okay, first let me go back to this pentagon over here. Remember that the interior angle going around a point, that would be 360 total, right? So how much is this angle of the triangle right there? It would be 360 divided by 5, which is 72. Okay, that means that one of these little parts is 36, right? Half of 72. Now with that number, And knowing that this part is 7 because it's half of the bottom of this big triangle, now I can look at this as a right triangle and I can use trigonometry to calculate this right here. So basically, let me just erase the irrelevant stuff. I don't care about that. Okay. I want to figure out h. That is the adjacent side to this 36, and 7 is the opposite side to that 36. So what trig function puts together opposite and adjacent? That would be tangent. Remember TOA? Remember SOHCAHTOA, right? So tangent puts together opposite and adjacent. Opposite, adjacent. All right, let me make some space over here. I am going to, now you know where we're coming from. You've probably got that written down. I'm going to do this calculation. The tangent of the angle 36 is equal to the opposite side over the adjacent side. So I'm just going to write that down. Then I'm going to fill in the opposite is 7 and the adjacent is h. All right, h is in the bottom of the fraction. I can take these two and I can basically swap them completely. I tried to teach you that shortcut when we did this at the beginning of the virtual instruction days. I don't know how much you guys really kind of absorbed back then, but it is valid to just swap them, and this is really looking messy. I'm going to try to write neater. Tan of 36. So, I mean, you could go through the process of multiplying both sides by h and then dividing both sides by tan of 36, but what you end up with is just swapping those two, and now h is equal to 7 divided by the tan of 36. And as long as your calculator is in degree mode, not radian, you can type it in, 7 divided by the tan of 36, and the answer is 9.6. Okay, so that's the height of this little triangle, 9.6. That's what's going to go over here, 9.6. Now I can do the area of this entire triangle is 1/2 its base of 14 times 9.6. So basically 7 times 9.6. And that would be 67.2. Now, that's only one of the triangles that makes up the entire pentagon. Remember, that's like this part of a 5 triangle figure. So the area that I'm going to plug in here is going to be 67.2 times 5. All right, which is 336. Whoa, getting too close to the top there. And I know this is really messy, but if you followed that roundabout explanation, we now have the surface area of the entire pentagonal prism. It's 560 plus 2 times 336, because 336 was just for one of the pentagon bases and there are 2 of them. So the total answer is 1232, and that would be square inches. Okay, it was quite a process. Now you'll notice I showed you how to find the surface area of triangular prism and pentagonal prism. These were not your basic rectangular prism calculations. This is high school geometry. This is how it gets complicated. But the same formulas applied to both. Lateral area is the perimeter of the base times the height of the prism. And then the surface area is just that plus the 2 base areas. But you have to be able to calculate the area of the specific individual type of base to plug that into that formula. So that's how we do it, to have one generic formula that works for various shapes. Okay, now we're going to move on to pyramids. All right, example 3 is a square pyramid, and we are to find the surface area of that square pyramid. We are going to recognize that the surface area formula has lateral area embedded in it, so we first have to calculate the lateral area, which is the walls, and then add the base to it. If this was like a three-dimensional solid pyramid that we could pick up and turn around, and we wanted to cover every side of it with something, then we would want the complete surface area. If we were just trying to paint the upright parts of the outside of it, it would be the lateral area, the walls. Okay, you'll see those formulas on the page where it describes pyramids. But there is a new variable here. It's like a lowercase script L that stands for slant height. That's this here. Lowercase script L is slant height. So to find the surface area of a square pyramid, let's start with lateral area. We have to do 1/2 the perimeter of the base times the slant height. Okay. Well, the perimeter of this base, since it is a square pyramid, shouldn't be too hard. The square has a side length of 18. So the perimeter, I'm just going to kind of come down here, lateral area equals 1/2 the perimeter times the slant height. The perimeter is just going to be 18 times 4, which is 52. Sorry, 72. Okay. Filling that in. Now the slant height is not labeled with a number on this diagram. What they have given us is the altitude of the pyramid is 24 meters. This red dotted line going from the vertex of the pyramid down to the center, that's considered the altitude. That is not the same as slant height. But we're in luck because the altitude, if you connect that to a segment going from the center out to the middle of one of the edges, and then you look at the slant height, those three, if you were to kind of cut through this, they form a right triangle. And the bottom here would just be half of the entire side of the triangle. So that would be 9. This is 24. And the slant height can be calculated using Pythagorean theorem. So 9 squared plus 24 squared would equal the slant height squared. So that would be 81 plus 24 squared is 576 equals L squared. 576 plus 81 is 657. Now we take the square root of both sides to get L by itself, and L equals the square root of 657, which is approximately 25.6. Okay, there's my slant height, and that is what I'm going to put here. Okay, 25.6. So my lateral area is basically 25.6 times half of 72, which is 36. So the final value for lateral area is 921.6 meters squared. That's just the walls. Okay. Now the surface area, thankfully, this is a lot simpler than the last one. Since the base that we have to add to the lateral area is just a square, so easy to find the area of the base. The lateral area is 921.6, and we have to add the base, which is 18 squared, because the area of a square is just the side times the side. So 18 squared is 324. So 324 plus 921.6 gives us a final answer of 1245.6 meters squared. That's our complete surface area of the entire figure. I don't know why it will not write the edge. Okay, there we go. Okay, let's dive into example 4. A pentagonal pyramid has a slant height of 17 inches. That would be this height that goes from the center of one of the base edges up the side of the pyramid to the vertex at the top. That's what the slant height is defined as. Okay, they give us the altitude is 15, so that would be this red value in there. That would be the height of the pyramid. What we don't have is any information about the side length of the pentagonal base. So we don't have the perimeter of the base, which we're going to need, but we can connect these two together and recognize that this would be a right triangle. If I draw it all in red, this red triangle, we can calculate the missing part right here. We'll call it A, all right? I'm going to do that. All right, so I've put the Pythagorean theorem into practice, and I've calculated that A equals 8. We're probably going to need that for something. All right, but let's get back to the lateral area and surface area formulas. We're supposed to find the surface area, but that starts with finding the lateral area, which is the area of the walls. Lateral area for any pyramid, according to the formula, is 1/2 the perimeter of the base times the slant height. Now, we do know the slant height is 17. What we don't know is the perimeter of the pentagon. But this little A value is going to help me find that. Okay, so I'm going to draw just the pentagon. It's a regular pentagon, and this segment is 8. Okay, now, once again, this is still a pentagon. It's just like the last one. I don't have to redo those calculations. I know that this is going to be inside there a 36-degree angle. I know that this segment is 8, and I know that this is the thing I care about down here. I'm going to call it like P. It's not the entire perimeter, but it's a part of the perimeter. So to calculate P from having, and 36 is this angle here. 8 is the side that's adjacent, and P is opposite in a right triangle. So I'm going to do the tan of 36 equals P over 8, opposite over adjacent. And this time the unknown is at the top of the fraction. So all I need to do is multiply both sides by 8 to get P by itself. So 8 times the tan of 36 degrees, and that's going to be a calculator problem. 8 times the tan of 36 is 5.8. Okay, that's just this part right here, 5.8. To calculate the perimeter of the entire pentagon, I'm going to double that first. So I get 5.8 times 2 is approximately 11.6. That means each side of the pentagon is 11.6. And that means that the perimeter of the pentagon is, so I'm going to put that down here, perimeter equals 11.6 times 5, which is 58. Now I can plug that in for perimeter up here. That's going to be 58. And the L, the lowercase l slant height is 17. So the lateral area of this pyramid is 58 times 1/2, or divided by 2, times 17, which is 493. And these would be inches squared. So that's lateral area. And once again, surface area is just lateral area plus the base area. And the area of this base, once again, it's a pentagon. So I'm going to make a little room here by erasing my trigonometry. I know now that each side of this pentagon is 11.6. So I'm going to blow up this triangle. Okay. It's 11.6 there. And this up the middle, which would be the height of this triangle, is 8. So each triangle has an area of 1/2 its base times its height. So each triangle inside the pentagon, and there are 5 of them, has an area of 1/2 11.6 times 8. So that would be like 4 times 11.6, because you could just do half of 8. 11.6 times 4 is 46.4. Now, that's just for one of the little triangles in the pentagon. And a pentagon is made up of 5 of those triangles. So the area of the base is going to be 5 times 46.4. Okay. The lateral area is 493. This is really not looking so good. I'm going to try to rewrite that. 46.4. Okay, 5 times 46.4 is 232. So if I add 493 plus 232, I get a total of 725 inches squared. Nice and neat. I love that. Even though this was kind of a complex problem, the surface area came out to a nice, neat 725. Okay. Good job hanging in there for those. All right, the really difficult part of the calculations is over for this lesson, but there's a few concepts I'd like to just hit upon before we end, and that is, first of all, some polyhedron have all of their faces are exactly congruent polygons, and they are regular polygons that are all the same, and they all connect, and they make a really special kind of solid. We call them Platonic solids after Plato. Okay, he must have been the one who named them. Yeah, a lot of the old philosophers were mathematicians. Mathematics and philosophy went hand in hand back in the day. So Plato named these special solids, or they were named after him. Maybe he talked about them a lot. But anyway, a tetrahedron is a solid that is made up of 4 triangles connected. A cube is made up of 6 squares connected. An octahedron is made up of 8 faces that are each triangles. And a dodecahedron, I believe, is made up of 12 faces that are all pentagons. And an icosahedron, I believe, is 20 faces that are all triangles. Yeah, okay. Those are some of the Platonic solids. Pretty cool shapes. Okay, now there are a few other solids that we didn't get into today, but we will get into them another day. The cylinder, the cone, and the sphere. Okay, cylinder is very much like a prism because it has those 2 equal congruent bases, but they are circles, they're not polygons. And then they're connected not by rectangles, but one continuous curved surface that connects the 2 bases. So that's just a different category all by itself. A cone is a solid that has a circular base, and then the other face is a curved surface that comes up to a point. You know what a cone looks like. And a sphere is basically a set of points that are all in space equidistant from the given center point. Okay, you know what that looks like. Okay. Also in this section in the book, they talk about imagining that we could slice through a solid, and what would the intersection of the plane we use to slice? Think about like a big, did you ever play Fruit Ninja with the big machete, that video game where you slice through the fruit and it would open up in two and go probably splurt, juice, watermelon or whatever. But the cross section would be if you could neatly slice through something, what would the face of that cross section look like? So here they show a cube being sliced by a plane, and the cross section is the purple area, which is a square. If you slice it straight like that between the two bases, okay? But if you slice between diagonal edges, you could get a rectangle as the cross section. Okay, they have also slicing that's got cut off. Slicing a corner, you would end up with a triangle as a cross section. So you have some more examples on your page. I don't know why they got cut off on my screen here, but take a look at those and try to determine what would be the shape formed by the intersection of the plane slicing through the solid in the way that it shows in the diagram. Okay. Also, what we want to think about is that a lot of solids can be formed by taking a polygon and revolving it around an axis. Okay. These are called solids of revolution. And I don't know if you've ever decorated for a party using like paper decorations from Party City. You buy these things, they come flat, and you open up the package, and you kind of pull on one side, and you go like this, and you rotate it around, and it forms like a big, say, bell for a wedding, or maybe it forms a Christmas tree, or it forms a big, flower type of thing. It just kind of folds out like that. Same idea. You've got the solid of revolution, the axis, and it would kind of, if you were to revolve around that axis, what kind of shape would be formed? Here it shows revolving a rectangle around a vertical axis forms a cylinder. Okay, so think about in these examples that you see on your page, what would be formed if that shape, like the triangle, was revolved around or rotated around? It stays fixed on the axis point, but it revolves around and kind of traces out an area of space, carving out the area of space. What would be formed? Okay, try to visualize that. Okay, next you've got, I just want to show you, you do not have to do these, but this is some practice problems that I've done in the past with students at this point in the unit. We don't have time for everything. These are good problems to practice the surface area of a prism, okay? And then next time, I'm going to have you do problems like this 11.4, but don't worry about that right now. Today, the video, taking notes, answering the questions in the Ed Puzzle, that's your work, okay? So you've done a lot today. Hope you have a great day. Bye-bye.